Welcome back. So far, we have seen how we can estimate people's risk attitude or risk aversion behavior in through utility function estimation or various and through various protocols, experimental protocols. However, utility function is an abstract concept and it's often difficult to obtain data or information about people's risk attitude. There's also the question of like how after getting this information, how we can use this information into our actual decision making. A common approach in risk management, which has been used in finance, in economics, in environmental management, environmental economics, agriculture economics, which is a general choice rule based on stochastic dominance. The benefit of using a stochastic dominance principle is that it is non-parametric. It does not require explicit specification of an investor's utility function, or it doesn't require restrictions on the functional forms of probability distributions. Stochastic dominance criteria account for the entire probability distribution and employ general conditions for someone's risk preferences. Let's take an example. We have a landowner or a landholder who must have to decide whether to invest in forestry or agroforestry, denoted by F, or some crop, denoted by G, with cumulative net revenue distribution function given by f of x and g of x, respectively. If one of the condition is this first order stochastic dominance. So forestry dominates the crop alternative by first order stochastic dominance if and only if g of x minus f of x is greater than or equal to 0, with at least one strict inequality for at least one level of x, g of x has to be greater than f of x. Let's take through this example visually. Imagine that we have these two distribution where the blue distribution has a mean of $100 with a standard deviation of 10, whereas the orange distribution has a mean of $120 with a standard deviation of 10. Their income and the probabilities are shown on these two axes. So the spread are the same, but the means are different. That's what we are observing here. So these probabilities, we can also convert them into cumulative probability distribution, which would be shown like this, where the blue one is on the left of the orange one, f of x. What else we can observe from here is that g of x, which is the blue line, is always on the left side of f of x. We can also tell that you can use this cumulative probability curves to show or to see that what is the chance of getting a certain payoff or not. So here is an example. We are interested to know what is the chance of getting $100 or less under these two distributions. So with g of x, we have we have around 50% chance of getting $100 or less income. Whereas with f of x, the probability is very low. So in this case, g of x is dominating f of x. So this is just in the text, the same thing. If we take an income of $100, the cumulative probability of having an income of 100 or less is much lower for the distribution f of x than it is for the distribution g of x. Thus, if g of x is greater than or equal to f of x for all x, then f of x stochastically dominates g of x. In other words, anyone with a monotonically increasing utility function will prefer f of x to g of x. However, the distribution functions are not always so neatly placed. In some cases, they are overlapping. So the FSD criteria has an intuitive interpretation. If one investment alternative dominates another, every non-satiated investor with non-decreasing utility function will prefer the dominant alternative. But that is not always the case, as I have just mentioned. Here is an example where the distribution curves, the cumulative probability distribution curves have intersected. So even though FSD criteria seems reasonable, it is not useful in this case because it cannot differentiate or discriminated between the alternatives. So what we have to do? We have to use the second order stochastic dominance criteria. So if investors are risk averse in addition to insatiable, that is first derivative of utility function is greater than or equal to 0 and the second derivative of the utility function is less than or equal to 0, the second order stochastic dominance could be used to choose between investment alternatives. Formally, forestry dominates cropping in the SSD sense if and only if the area under Z of Z is greater than the area under F of Z, this is an integration that's showing that the area and it has to be greater than or equal to 0. The difference has to be greater than or equal to 0. In words, the SSD requires that the area under the cumulative density function for forestry is always smaller than the area under the cumulative density function for the crop. Every risk-averse, non-satiable investor prefers the investment alternative that dominates by SSD. So here we have plotted two graphs. The first one we already have seen, where we have cumulative probability functions which are intersecting with each other in the top graph. The bottom graph is showing the integral of these two distribution. It's reinforcing the concept or the idea that the one which has the smaller area dominates the other one which has larger area. So in this case, for a risk-averse individual, they prefer to avoid low income on the left-hand tail more than benefiting from the greater probability of relatively high income in the right-hand tail. So they would prefer f of x. So in summary, what we have covered in this lecture so far: the expected utility model, which are easy to calibrate but hard to apply. And then we have covered a stochastic dominance model, which are partial order non-optimization based process, which could be applied to messy functions to check for dominance. And in many cases, a visual check might be enough. Thank you.